Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, what is electronic skin? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is delving into the fascinating field of soft robotics. I'm finding out how a soft electronic skin can help improve the user experience for people with prosthetic limbs. But first, I'd like to remind you that you can send in questions for my future guests. And there are a few different ways you can do that. You can submit questions on the website at robottalk.org or on Patreon at patreon.com/Claire Asher. Or you can contact me on social media at Robot Talk Pod. So, without further ado, it's time for me to introduce this week's guest. I recently had a great chat with Miranda Lowther from the University of Bristol about soft, sensitive electronic skin for prosthetics. Today, I'm talking to Miranda Lowther, a PhD researcher at the University of Bristol, working on soft robotic e-skins for prosthetic limbs. Hi Myra, great to have you on the podcast.
Hi Claire, thank you so much for having me. I'm happy to be here today.
So to get us started, I thought we could talk about prosthetic limbs in general and what are some of the biggest limitations of kind of existing systems, existing designs in terms of the user experience.
Yeah, so there's, of course, a wide array of different prosthetic limbs that are available either commercially or being created in research that address multiple different limitations, things like, say, providing a user with the ability to have a sense of touch again, particularly for upper limbs, or giving more physical functionality, so being able to handle and hold and manipulate different objects, or also be durable enough to withstand day-to-day living. So, things like being able to handle, say, not just holding a pen, but also maybe if the individual works out, then, maybe actually being able to do that again. But there's also two other kind of quite significant areas that we could really do with looking at more. So in particular, how the prosthetic limb might look, but also how it feels when a user wears it. So, in terms of appearance, that's quite a big issue, particularly for facial prosthetics. And, typically people can either go one of two ways, where it's either they would understandably prefer it to look as similar to what they originally have had if they did not have this difference from birth, or it could be the opposite way, where they prefer to have, say, I don't know, like a bright purple eye for an orbital prosthetic or something similar, just because if somebody's going to be looking anyway, then maybe they feel better as a user that when they're talking to that person and they're not just trying to figure out what is slightly off. So most prosthetics in that area are very, very, very good. But comfort, like I said, comfort's a very significant issue also. So we typically break that down into a couple of different areas at the moment. So I do think that it needs to be investigated further. So these include the weight of the limb. So particularly for upper limb, that can be an issue, but we can all imagine wearing a really heavy shoe and walking with it. Also, the actual swelling of the residual limb, so the remaining limb. When an amputation occurs, this swelling can last for quite a long time, but it also can happen day to day when somebody's wearing the limb. So, obviously that can cause some discomfort, but also if it shrinks due to temperature, so it could swell due to increased temperature, but if it was too cold, then you could run the risk of your prosthetic falling off, which is obviously an issue. And also, of course, another issue is pressure. So one example I like to give normally is, everybody's worn really uncomfortable shoes at some point in their life, right?
Yeah.
You get really bad blisters, rubbing, maybe you're bleeding, and, say you've worn these brand new shoes to a conference or out for something. You kind of want to go and change them immediately as soon as possible, right?
Kind of can't focus on anything else.
Exactly. But obviously with a prosthetic limb, that is so much trickier to tackle because, you go through such a long process of acquiring the limb, and depending on the method of which you're obtaining it, either, here in the UK or in other countries where you might have to pay for that process, there's that additional financial burden with it. So, it's kind of difficult to actually address those issues, and it can be quite high pressure. And another kind of discomfort that occurs also is, of course, temperature. So, nobody wants to wear kind of like a very sweaty, uncomfortable sock or shoe, right?
Yeah.
Yeah, so those are some of the limitations that exist at the moment for users that are wearing a prosthetic limb. And some people, including myself, are trying to look into those issues.
So in your PhD research, you've been developing an electronic skin, which is intended to be used as a sensorized prosthetic liner. So can you tell us about this e-skin and how it works? Yeah,
of course. So prosthetic users normally wear a liner over the residual limb, but under the prosthetic socket. So kind of like when we put on sorry to bring up the shoe metaphor again.
It's a good metaphor.
But it's like putting on a sock before a shoe. And normally these are either fabric-based or made out of silicone. And so could we actually maybe find a way to measure all this discomfort and actually quantify how a patient feels when they wear a prosthetic limb? At the moment, there are some research projects over the past couple of years that have started to take a look at, maybe we can try and quantify this, but it's still a very open issue. When somebody goes through a prosthetic fitting, they'll be working with a clinician, and they'll be checking with them if the socket is comfortable or not, and there'll normally be a trial period where they test out the limb, and it can be optimized from there. Of course, patients are able to express themselves during appointments, but that appointment and the actual conversation that goes on about communicating that discomfort, because it's entirely verbal, it can be relatively difficult or require quite a significant amount of experience, or, almost like an intuitive sense of being able to identify based on the person's response where their discomfort is. And this can also be even trickier if they have experienced an amputation because of nerve damage. So to try and help with that kind of conversation and act as an aid for both the patient and the clinician, I'm looking at making a sensorized prosthetic liner. So rather than putting sensors, say, between the patient's limb and the liner that they're already wearing, or between the liner and the socket, because, they could shift, there could be damage. I was thinking maybe we could actually make the entire thing a sensor. And so this sensorized liner is made out of an electronic skin, and the e-skin itself is comprised of a network of channels that are filled with saline, so salt water. And when you press into these channels, the actual cross-section of the shape, if you can imagine that, changes. So if you conduct electricity through it, one particular equation that you can use then is that the resistance of a wire or any conductive material is proportional to the cross-sectional area and the length of this conductor, this wire. So if we applied this principle to anything that conducts, say this channel, because saline, salt water, conducts electricity, then we can equate the force pressing into it to a resistance value or impedance value.
Okay.
So then what we do is that we collect all these readings and use machine learning to then map these resistance changes or impedance changes to locations and sizes of forces. so that then eventually when this is used as a prosthetic liner, we can actually get some kind of mapping of where, say, particular forces have occurred over repeated timeframes, and get a better understanding of where these kind of sources of discomfort are occurring. And one of the beauties also of this technology is that because it's using just silicone and salt water, it's something that's biocompatible and, limited risk in terms of somebody not being able to wear it.
Yeah.
And also relatively low cost and, not using off-the-shelf kind of technology that could risk being damaged through wear. And it's also made using materials and processes that are similar to people who work in reconstructive science already use. Okay. So I have kind of an industry mentor, and I keep in touch basically with a team of prosthetists at Southmead Hospital, so the local Bristol hospital, and have used their manufacturing processes to inspire the manufacturing process for this, so that we can actually not only have a sensor that can work, but also has less limitations to hopefully be deployed eventually than other technologies.
So they already have everything they need to make it in-house?
Yeah.
Okay. And so would the idea be that this would just be worn for like a limited period of time when you're first trialing a prosthetic limb, or, would that continue in the long term?
Yeah, so that's a really interesting question. So to start with the technology as is, it's primarily for the initial fitting process, basically. Or maybe when a patient is, say they've been wearing the limb for a while and start to have issues again, maybe it can be reused in those instances. But yes, that is kind of the main aim.
Yeah. But I mean, this kind of technology in principle, the ability to, detect forces on a flexible material and know where those forces are happening, seems like it would have quite broad potential applications as like, as an e-skin in other uses. Can you talk a little bit about what potential applications it might have in the future?
Yeah, so of course, I've kind of primarily focused on this for prosthetic users and kind of very much designed it with that in mind, that it's working towards this. But of course, one natural extension of that would be kind of healthcare related applications or wearables, where you can maybe have almost like a suit that you could kind of measure deformations on. So say for bed sore management. It could also be used to better understand how we interact with other materials or clothing. So like I mentioned with shoes before.
I was just thinking that actually,
Yeah, it's like smart insoles to kind of better understand how we distribute our weight when we walk. And one application could be posture monitoring. So, of course, as we all age, we all become more and more aware of our posture, and we could possibly use that e-skin as a way to kind of be able to monitor how somebody is sitting if we replaced a cushion with it. So, yeah, there's multiple possible areas there. It could also be used for exploratory robots, so in place of tire treads possibly in the long run, for exploratory vehicles. So say if you wanted to get a measurement of kind of the texture of the surface underneath, kind of like an imprint. And yeah, also the beauty with e-skins is it's that step towards a more biologically inspired system that might appear less unnerving or less intimidating possibly to the people who aren't specialized in this area. So there's also possibility for e-skins to be used in kind of actual humanoid robots or in, say, robot arms that we see in real life or in industry to kind of help improve public perception of robotics. And one other one could also be art and, human computer interfaces. One beauty of this is if you kind of view it as almost like a homogeneous system that you could interact with, it could work really nicely in terms of like almost a touch screen. Eventually. Because how you design this network of channels, you can change from there how it responds to the sensing.
Right. Okay.
Yeah, almost like it's its own little computer, so to speak.
Yeah. That leads really nicely into something else that I wanted to talk to you about, which is the concept of morphological computation, which I must confess I've been a little bit sort of obsessed with ever since I interviewed Helmut Hauser back in season 3 of the podcast, and he kind of blew my mind a little bit with this whole idea. For listeners who aren't familiar, morphological computation basically means that the shape or structure of something, of an object, means that it behaves in intelligent ways. I hope that's a reasonable, brief description of it. But, could you talk a little bit about how you're using that in your research?
Yes, of course. I was very much inspired by Helmut Hauser's work. He's actually my supervisor. So, like you said, morphological computation is such a fascinating area, and it really is kind of that key to that next step of having more bio-inspired technology, right? It's that idea that biological entities or systems do very clever things without requiring a brain to do so. So one perfect example is all of us probably have experienced calluses on our feet at some point. So that's something that we don't necessarily think about doing, right? But our body just locally does for us as a form of protection.
Yeah, that's true, yeah.
With morphological computation, if you design something in a different way, you can design in such a way that it has its own internal intelligence to it. So it can respond to a change in environment in a clever way, whether that's in terms of actuation or through sensing. So when it comes to my sensor, the beauty of it is that the actual structure, how my sensor is designed, if you change it, you can change how the sensor responds to forces, so you can improve it from there. Because of how we use the sensor, rather than trying to very accurately depict, if we place a channel here, it results in this output, we rather take a step back and think, okay, if we view this as a black box, so to speak, and use some machine learning, maybe the machine learning can map how the sensor responds to these forces, to the actual, perceived locations or sizes of forces. So that's another area that is related to morphological computation, is this more kind of taking a step back, and rather than trying to replicate everything down to the tiniest grain in terms of inspiration, viewing it more like how things work in nature. Like with evolution, where, it just happens. Yeah. Right? It doesn't require any thought process to it. So that's how it kind of is used in my design. But there are many ways that it could be used also in future. So like the way that you design the channels, you could design it such that maybe it's more sensitive in certain areas than others. But also, in future, one area that we could look at is how we structure the actual silicon aside from the channels, to see if it could deform in a different way, so that maybe it becomes stiffer or softer in response and can better protect the limb that it's covering. But also beyond that, morphological computation is already used in other areas of prosthetics. For example, with self-adjusting prosthetic feet for lower limb prosthetics, and energy recycling is another example.
Okay.
Yeah, it's definitely, I feel like, the key towards getting to a point where not only are we able to use robotic technology in a more seamless manner with morphological computation, especially within prosthetics, but also tackle issues such as weight. So, if you had an actuator that could also be sensorized or vice versa, that significantly helps, or, reducing the amount of power required to run a particular system. But it could also, like I mentioned earlier, help with public perception. If we can see something that is more similar to us and something that we can intuitively understand, then maybe that will help, hopefully, with public perception of robots.
Yeah, absolutely. And I guess, obviously I'm not a prosthetic user, so I don't know what that experience is like, but if your prosthetic limb was able to respond to the environment in intelligent ways without you having to think about how to make it do that, like, that kind of reduces the cognitive load on people who are using a prosthetic?
Yes, absolutely. And also to be able to, as I mentioned earlier, to be able to provide functions that this kind of technology doesn't currently have. So, for example, being able to respond to not only touch but heat, or being able to identify if maybe their residual limb is too warm or too cold, or if the prosthetic limb is coming into contact with something very hot.
Yeah. You just made me think, does temperature impact your e-skin at the moment? So, like, does that affect the conductivity?
No, it doesn't at the moment. So that's one of the beauties of this system, is that it's so, in some ways, simple, like chemically simple, in the sense of there's just silicone and there's just salt water, that there's minimal impact in terms of, or minimal considerations about, if this chemical interacts with this chemical. But yeah, in a similar vein with temperature, as you've mentioned, because salt water, its boiling point is over 100 degrees, we currently believe that, there shouldn't be much impact.
Okay. We had an audience question from Kevin on Blue Sky, who says, what are the biggest challenges with soft robotics? Oh, nice broad question there for you.
Soft robotics. Well, I would say soft robotics is an amazing area, and obviously still very young in some respects, in terms of there's a lot of things that we need to address. And yeah, some of those would include being able to have some predictability to soft robotic systems, because inherently soft materials, as we can all imagine, don't always perform in ways that we would expect. Say with the balloon, if you inflated it, it might not inflate in the same way if you re-inflated the same balloon twice, right? But as a result, being able to apply traditional techniques such as simulating them, that's one big limitation. There are some good simulators that exist, but of course it's still quite tricky to be able to simulate these materials. That's being explored at the moment. And also being able to control such unpredictable materials and systems. Of course, that's one beauty of morphological computation, is if you take a step back and you kind of control the system in a more bio-inspired manner, or, more that black box principle of just accepting that this mechanism performs in this manner. But traditional control techniques, as a result, don't specifically apply. So that is another limitation, so to speak. Another one would be on a more kind of transition from research to industry, is probably accessibility of materials.
Okay.
So there are some areas of research where we're using very low cost accessible materials, of course, like with my sensor with saline and silicone, or, there's research programs looking at using edible robots.
Cool.
Yeah, which is very exciting. But on the other hand, there might be certain cases where, say, carbon black is being used, which can be carcinogenic,
right.
Or materials like electroactive polymers can be quite difficult to procure. So then applying that to actually scaling those and using those in industry could be a limitation also. And one final one is one of the beauty in soft robotics is that because it crosses so many different disciplines, we, work with a wide variety of different people. But I think one interesting area, not necessarily a limitation, but an area to explore, is collaborating with those more in the arts. So those more experienced, say, with different areas of craft or conductive fabrics or e-textiles, so electronic textiles, more so working with maybe seamstresses or people who work in fiber arts, so things like knitting or crocheting. For example, crochet actuators are one area of research that exists, and, very interesting melding of two different disciplines.
Yeah.
So I wouldn't necessarily say that's a challenge, but it is one area that we could definitely look to explore even further, is going beyond kind of working across disciplines, maybe in like chemistry or, obviously medicine, but also in those who have significant expertise in more dexterous and hands-on areas. Who are very much like knowledgeable and experts in that field.
Yeah, definitely. I mean, I guess maybe the challenge there is that there isn't enough collaboration and conversation between science and the arts in general, right? And that's kind of instilled from early on in education, when it's like that's just kept so separate for no good reason as far as I can see.
Yes, absolutely. I completely agree. And it's very bizarre to kind of go through that process of pursuing a career in science or STEM and then coming out to more of a research end and then realizing that that inherent creativity that we all have as people is actually something that we really should be nurturing, right? And yes, in soft robotics, that's also an amazing thing, is that we have a lot of very creative people who have a lot of different creative outlets, including, like I said, with knitting and crocheting, but also things like building furniture or painting. But it's definitely something that, if there was one thing I could tell somebody at the start of their education in like secondary school, definitely would be something along the lines of cultivating their creative side.
And then we had one more audience question from Katie, also on Blue Sky. Katie says, how do you intelligently actuate soft robots?
Yes, so that's a really, really interesting question, Katie. I'm interpreting what you're referring to as intelligently actuate as being able to actuate a soft robot in a better way than perhaps we traditionally would. So, you know, one big way is perhaps to look at not just the actual how we actuate them, but what those actuators are in the soft robot. So as I mentioned before, sensorized actuators could be a really great way, because you're using materials that you're already using anyway to make the actuator. And it also reduces weight and the level of complexity of the system, ideally. And that will help generally overall for the system. You can also consider how the information, so if we define information as, say, the sensing signals or the way in which you're telling an actuator to move is transduced, so translated from that one form of energy to the other. So, for example, with mine, I'm transforming that kind of physical deformation into electrical information, which is then being used. Understandably, it's a sensor, so it's not exactly the same. But similarly with other soft robots, it's kind of taking that physical response and translating that into an electrical information. And that could be a really great way to consider how we intelligently actuate soft robots. Is there a way that we can do that either with simpler level of information required or less complex processing, or even locally, so more like morphological computation, where the system could respond immediately in that small area. Say a robotic hand was damaged, then a form of self-healing where it could respond and improve and basically heal itself from that damage would be fantastic. Not quite actuation, but could be similarly if you applied that to an artificial muscle. Another thing could be coupled or multimodal systems, so sensors or actuators that can perform multiple different things, either through sensing multiple different types of information, so say temperature and sound, or being able to have an actuator that can move in multiple different axes. So not just like a typical group of muscles where we only actuate in one axis, perhaps. Maybe they can be designed so that it can move in multiple different directions. My interpretation of intelligently actuating soft robotics, one great way could be actually considering how we can use how one particular part of the system performs as a way to interact with another part. So maybe it's a form of communication between a sensor and an actuator, or perhaps it's more like the human agonistic-antagonistic muscle pairing, where we kind of use those pairs to achieve the ideal amount of actuation required and have better control.
Yeah, really interesting possibilities there. As you were talking, my mind was bringing this whole conversation together into one idea. So this is a little bit out there, but if you could use the sensorized actuators you mentioned in the prosthetic limb liner you've been developing, could you solve the problem of when the residual limb, say, shrinks or grows in different conditions, to then sense that it's, say, shrunk, and then make the prosthetic liner like get bigger to fill that void so that the prosthetic limb still fits.
Yeah, so that's a really interesting possibility. And there's actually one similar example of this. The group of researchers created a system that used air pockets to adjust the pressure when it was worn over a residual limb, so that it could provide more or less pressure in response to how much force was being applied to it by the leg. Cool. So that's one example where that kind of idea could be used. But yes, it could be used in a similar way with this sensor, absolutely. And you could also look at how it's designed to kind of provide into the design itself that ability to swell, or maybe even have channel systems so that more material could be provided, so that it could expand in that area, as you mentioned. Yeah, absolutely.
Cool. Yeah, I mean, I appreciate that's one of those much easier to come up with on a podcast than it is to actually implement. But,
well, you say that, but that's the beauty of morphological computation, is that it does. While you're saying that it's something that might not be feasible, it's something that, it does exist in nature.
Yeah.
And who's to say that we can't develop something like that in the long run?
Yeah, absolutely. Myra, it's been so lovely speaking to you today. I've been chatting to Miranda Lowther from the University of Bristol. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @Robot Talk Pod on social media to see a photo of the sensorized e-skin liner for prosthetics users that Myra and I talked about. I thought you might like to hear a sneak peek of this month's bonus episode.
And one of the other things there is about the system not being deceitful or misleading or pretending to be sentient, which can happen, particularly with emerging humanoid robots. And people get a misconception of what it can actually do and what it can feel, what it knows about you and how it's responding to you. So trustworthiness is about trying to avoid that.
Yeah.
And again, just one last point in the context of assisted rehabilitation robotics, it's about ensuring that there has been expert clinical oversight as part of a rigorous testing and validation process. So the person using that technology need to be assured that somebody's verified the performance in different situations.
Yeah. I guess that deception aspect you mentioned is not just in terms of, I mean, if it's a robot that can talk to you, it's not just in terms of what the robot says it can do, but also in terms of like the marketing and the way it's kind of sold, right?
Yeah. And how it's referred to as well. So, there is a tendency to call robots he or she, etc. And that sort of brings with it the baggage of expectations.
Yeah.
I really like how the task program framed up the kind of issue around trustworthiness in principle and trusted in practice. And that's what you mentioned also, Claire, earlier. And so from my perspective, this trustworthiness really refers to objective measures and standards that ensure the safety and other critical functions in relation to autonomy. And this can be done through verification, validation, and testing. But on the other hand, so systems that are trusted in practice, I think is more about the user's perspective. And so perceived safety, for example, comfort and confidence in the system. And I think both are really important to realize. And this has been both really emphasized within the program. So making systems not only safe, but also make users feel safe.
Yeah, absolutely. And I mean, if we're talking about robots that are being used by members of the public rather than, like specialists, I'm not reading some safety verification certificate or whatever. Like those kinds of things, while they're important, they don't necessarily make me trust a robot as much as like seeing that it does what it says it's going to and is reliable?
Yeah, over the last 4 years, I've seen an evolution in the notions of trustworthiness or trust in robotics and AI in general, right?
Okay.
And we can see this in the data. So we are going to soon publish a report which we co-wrote with Digital Science that shows how the field of trustworthy autonomous systems has evolved over the last 4 years. And you can see a clear disconnect in the community very early on, back in 2020, where trustworthiness was understood by the computer science community differently from the human-computer interaction and other communities, the social sciences. They were very disconnected communities, talking about trust and trustworthiness in very different ways. And over the last 4 years, and we show this with the work that the community that we have funded has done, so the connections we've created across the community, you can start seeing more human-centered approaches around the definitions of trust. So it's not just a pure verification and validation approach to trust, but also takes in, as Lars and Praminda are talking about, the human elements in the definition of trustworthiness.
If you'd like to hear more from this bonus episode, sign up as a supporter on Patreon by going to patreon.com/Claire Asher, and you'll get access to the full catalogue of bonus content. Next week, I'm talking to Will Kinghorn from Made Smarter about robotics for small manufacturers. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.